So let's continue with what we are doing. So we already installed a distillation column, and then in order to remove hydrochloric acid from the other two components in the stream 20. So in the stream 20 what we have is vinyl chloride and a very trace quantities of hydrochloric acid, and then we have ethylene dichloride. Okay, so what we need to do is we need to purify this stream so that our target is to get a 99.5 percentage of vinyl chloride. So if you remember, I showed you, sorry, maybe I'm going to show the PowerPoint. So ethylene dichloride, it's the less volatile compound, so this should be our heavier component, and then vinyl chloride monomer is the lighter compound, so this should goes to the top of our column. Yeah, so let's try to do that. So I already showed you how to deal with a distillation problem. So let's start with adding a component splitter. Okay, so let's repeat what we did before in order to get some information which is required to design a rigorous distillation column. Yeah, so let's add the component splitter. So this will be like a nice practice for you. So we're just repeating the same exercise again, but this time our goal is to separate vinyl chloride monomer from the ethylene dichloride. So ethylene dichloride is the heavier component and vinyl chloride monomer is the lighter component. Okay, so where is that? Let's click separator. So we need to add a component splitter. So now don't add the separator, this is a flash separator. So add component splitter, just click it here, add your stream 20. So by this time I know you will design distillation column very easily, just to follow the lecture videos carefully and then try to solve one by one. Yeah, unknown splits. So this time we need so this is the lighter component, vinyl chloride monomer in the top. So vinyl chloride monomer, so let's put 1 and everything else is 0. Okay, that should be perfect. And then parameters. Okay, let's put both the stream have the same pressure, so equalize all steam pressures, and then let's put vapor fraction is equal to 0. So we are at the bubble point, so this is converged. Okay, so close this one. So let's put 21, 22 here. So this is really a very big process flow diagram. Okay, 21 and 22. So just right click and then click show table. What we have here, so okay, this is very high. Right click, show table. Okay, not bad. We have to maintain. So this is at a 79.49. Okay, and then so our exit temperature is at 100 degrees centigrade. So this is our reboiler temperature, the stream. So one thing we can do, let's delete this. Let's press OK. If you go back to our PowerPoint, so even at say like again at a 10 bar, or we can clearly separate the fluid. Yeah, so or maybe we can even go at 5 bar. So clearly there is clearly vinyl chloride monomer will be in the vapor phase and this will be in the liquid phase. So let me draw for you. Maybe I may choose some nice color. Okay, I don't know how to change. So follow this light blue now. So what we have here, so if you see the, if you put the pressure at 5 bar, 5 atmosphere, so if you go, so clearly you can see that your vinyl chloride monomer boils roughly at 40 degrees centigrade, whereas your the ethylene dichloride, it will start, the bubble point temperature is almost near 80 degrees centigrade. So we have good big difference between the bubble point temperature. So let's keep the pressure to 5 bar, and then let's fix the temperature to 20 degree centigrade. Okay, and then the inlet stream, and then we can add the component splitter. So why are we going to do that? Just to make sure we are in the economical distillation zone, so that our condenser pressure should be okay. It was not a bad in fact, but let's try to decrease the condenser pressure to nearly to 25 to 49. Let's give a try. Okay, so let's add press all, let's add a cooler. So select, add inlet stream is 20, outlet stream is 21. Let's put QE maybe 8. I don't remember that any. Okay, QE 8, 21. Close this value, close this, and then put the temperature to 20 degree, pressure of 5 kilopascal, 5 atmosphere. Okay, so this is perfect. Okay, so now we can add the component splitter. Let's try now. Component splitter, and so again we are collecting the record level of information to design the rigorous distillation column. So we need the condenser pressure, temperature, reboiler temperature, number of stage, feed stage, condenser temperature, reboiler temperature at some fixed pressure. In this case, now we are fixing that at 5 atmosphere. Okay, in both condenser and reboiler. So let's go to Aspen HYSYS. So let's put overhead steam 22, bottom 23, enter it, and parameters, vapor fraction is set to bubble point. So because we will have vapor in the distillate, yeah, so we set it to bubble point, and then splits. Let's if you look back the graph here, so we will have vinyl chloride monomer in the top. So this is the less volatile compound between these two. Okay, between ethylene dichloride and vinyl chloride monomer. If you compare the bubble point, vinyl chloride monomer is the more volatile compound, so it should come on the top. So vinyl chloride monomer, press 1, and then remaining are 0. So this part is okay. Go to parameters, equalize the stream, converged. So let's take a note of the properties of the fluid in the stream 22 and 23. So just click and then press show table. Again right click and press show table. Parameters, vinyl chloride monomer in the top. Okay, this is not a great idea, so let's increase the pressure to 20 atmosphere. Okay, see, something is not correct. Okay, the bottom vapor phase fraction is set to 0. This is not correct. So let's delete this. "21, 22, 23. Close it. Let's click select and then vapor phase to 0. And then 23. Vapor phase to 1. So this is at the dew point. Close it. And then properties. So double click. Go to parameters. This is at 0. This is at 1. So we have to. So we set the bottom set to vapor fraction to 1, which means at bottom is at its dew point, and then top is equal to 0, which means this is at its bubble point, the top stream. Okay. So split is equalize the stream. I don't know whether I said this before clearly. So the top should be at its bubble point, the bottom should be at its dew point. So vapor fraction is 0 in 22, vapor fraction is set to 1 in 23. Okay. Utilize all streams, go to connections, blah blah blah, 21, 22, parameter, splits, and then in the top we are expected to see vinyl chloride monomer. Let's put 0, 0, 0. A consistency error occurred. Unknown overhead pressure. There is some problem. Let's fix it. So whenever you have some issues, let me delete it. Let me delete the stream and then press the button here active. So it will converge. Let us do it again, or maybe let's change the temperature. So this is at this is very tricky now. It's taking a lot of time as well. Just checking what to do. Maybe let's close this. Let's check what's this pressure to. 15 kilopascal temperature. So the recommended value from the literature, it's by the author Goodrich, preparation of vinyl chloride. Okay, it's not this one. It's from Goodrich. I couldn't find that patent. Send it to the BF Goodrich company. Sorry, yeah, I think this one. I think they used some value. They used some specific value of what's the value they used. Let's check. So they used 4.8 atmosphere and 20 degrees centigrade. So let's try to fix that. So let's change this to 20 degree and then let's put it to 4.8 atmospheres. So this is from the literature value, 4.8 atmospheres. Okay, and then let's add the component splitter and see how it works. So let's take stream 21, overhead 22. So we are trying to solve the problem by doing what we know to do. Close this value and then double click and then put parameters. So our top should be set to bubble point, bottom should be set to dew point, and then equalize all steam pressures. Go to splits. In the top we expect to see vinyl chloride, and then everything will be 0. The simulation is over specified. Unknown overhead pressure. So something is not fine. So I'm going to pause recording the video. I will try to solve it and then I will continue to record this exercise. This is something tricky. I need to check, make sure about the fluid properties, and then I need to check why I cannot separate the, or what's this error. It says something is over specified. I can check it now. So give me some time. I will try to fix it and then I will continue to record this lecture. I don't know what's the problem. So let's continue with our lecture. So honestly I didn't find any mistake. I just repeated and then for somehow it worked well. So let's check. Let me do the same. So we are in the stream 21. So if you double click, or maybe let me do one thing. I will create a table for this stream, show table. So 10 degrees centigrade. Oh, what's this kilopascal? So let's put this at say like 10 kilopascals. So 10 atmospheres for the moment. Okay. So now let's use let's assume we need a distillation column to separate vinyl chloride monomer from methylene dichloride. So let's follow the same rules. Bring your palette, go to separator, click your component splitter, add it. I think this time it should work. So select 21, 22, bottoms out 23, go to parameters, put here 23. Let's keep the bottom one at its dew point, press 1. So follow this procedure, put the dew point to 1, click equalize all stream pressure, and then here you need vinyl chloride in the top, which is 22 here, and everything else should be 0. Okay, let's try how it works this time. Okay, so everything is converged, and if you go to parameters here, 22 is 0, which means this is at its bubble point, and at the bottom is 1, which means it is at its dew point. So this works perfectly fine. So what you do is, like, this is what I realized. So sometimes when you put here 0 and instead of filling here 1, so it automatically do something else, which maybe I can show you one time. I will close this. Let me delete it. So let me tell you what I am talking about. You add a component splitter, add 21 here, 22, 23, okay, and then parameters. If you click here, vapor fraction 0, so which means we are setting the top at its bubble point, and then if you go to splits, go to 0 0 0 0 0 0 0 0, finally 1, obviously unknown overhead pressure. Okay, let's equal all stream pressure. So one thing I don't like here, this way you see here stream 22 and 23 both are its bubble point. This is something that we don't want. Yeah, the bottom should be at its dew point and the top should be at its bubble point. So this was the problem that we were facing before, and so take a note in your notebook so how to deal with this type of issues. So when you encounter some problem like that, just add a component splitter. Everything else is same procedure. 21, yeah, okay, sorry, oh, I did a completely mistake. 22, 23, and then here go to parameter. First select your 23, which is your bottom, and set it to dew point, so it will automatically change this one to bubble point. That's what I realized. Splits 0 0 0 0 0 0, and finally we need vinyl chloride monomer in the top. Press 1. Overhead pressure, okay, equalize all stream pressures. Now we got what we exactly need. Okay, I think this looks perfectly fine to me, in fact. So stream pressure here is at 94. So what we have here, so if we click here in the 23, we can see, go to composition, the liquid phase, we have ethylene dichloride. Okay, here we have the top we should have a vinyl chloride monomer. Okay, so I'm happy with these things. So what we are going to do now, so let's create a show table. So 21, so we see here in the top condenser temperature is -179, so clearly this is not an in the economical distillation zone. Bottom is 10, this is okay. So we will try to make the condenser temperature somewhere around 25 to 49. Let's try. Maybe it may not be possible, but we can try. So what I'm going to do is first I'm going to decrease the pressure. Let's put 5 kilopascal, 5 atmospheres. 5 atmospheres, and you see there is a slight decrease in the temperature. So let us slightly increase the temperature. Go to 20. Okay, not bad. So 30. When I press 30 degrees centigrade, you see the condenser temperature is slightly increasing. So let's put 60. Okay, this is a perfect one. You see the condenser temperature is in the economical distillation zone, 33.52. So this means we can use a normal river water to condense your stream that comes in the top. Yeah? And then in the bottom, in the reboiler temperature, it's only around 60 degrees centigrade. A medium pressure steam is more than enough to create such a temperature. So I'm happy with this condition. So let's close this. Let's take a snapshot of this. Okay, that's so take a snapshot of all these conditions. No, we have to also let's close this. Let's also add a table for stream 11, stream 21. Sorry, what is this show table thing? Hide table. So 21 is already here. Okay. Oh my god, I think I'm doing some mistake. Let's see the 23 show table. Okay, sorry 21. Once we set it at 60 degrees centigrade and 506 kilopascals or 5 atmosphere, I see here we are in the economical distillation zone. The condenser temperature is 33.52. We can use a river water, and this is, we can use medium to high pressure steam in order to create to maintain 147 degrees centigrade in the reboiler. Okay, so this is something we should be very happy with. So let's add a snipping tool. So let's copy this in our PowerPoint. So this is something I tried. Let's delete all these things. So 22, and then now we we go to the shortcut distillation column. Okay, so let's delete all these things. Press delete tree. Where is your shortcut distillation column? It's here. So just add the shortcut distillation column. Add your input stream 21, distillate is 22, bottom is 23. Let's call the qcond 2, qrib 2. So press what's the problem now? Okay, looks fine to me. And then go to parameters. So light key in the bottoms, that should be 0.0, like a fraction of light key in the bottoms and fraction of heavy key in the distillate. So what is the fraction of heavy key in the distillate? So heavy key in this case is an ethylene dichloride. Okay, so we have only a very tiny fraction of this in the distillation, and then we have only a very tiny fraction of vinyl chloride monomer in the bottom. Okay, so which means all the remaining vinyl chloride monomer will be in the top, vinyl chloride will be in the top, and all the remaining ethylene dichloride will be in the bottoms. Okay, so condenser pressure, let's go back to our slide. It should be 5 atmospheres. So 5 atmosphere, 5 atmosphere. Reflex ratio, let's put 1.75. Okay, let's close this. So everything is converged. So let's close this and then let's check what's the new temperature. So take a note of, like, right click show table, right click show table, right click show table about the column. So this is the column conditions. So just to double click on the column, add, but is there anything called a reflex ratio? Nothing. So top product phase, external reflex. Let's close these values. So minimum tray. So let's close all these things. So we have 22, that's our top, and then bottom. So again the temperature is 33 and the bottom is 148. The number of trays is around 9, and then feed enters at 4th column, roughly 4th stage, and then minimum reflex is 0.1513. So I think I'm happy with all these things. So let's take a snapshot. Let's see how it works this time. So we should get 99.5% of pure vinyl chloride monomer. So that's why we are doing all these things at the moment. Okay, so let's save this stuff. So I will upload these details. So this is for distillation column 2. Tired. So let's check. So now we have all the information required to go for the rigorous distillation column. So let's close this one. Okay, let's close this. So now it's time to add the distillation column. So add the distillation column, connect it to stream 21. So total reflex, overhead liquid product, let's call it as 22, simple. 23, again this one qcond 2, qreb 2. We can give any name, yeah, for here. Press next. Oh sorry, go back. So the number of stages is 9. number of stages is 9, and let's say it enters at 4th tower, and then press next. Condenser pressure, go back to your PowerPoint slide, 5 kilopascal, sorry, 5 atmosphere, 5 atmosphere. Press next. Temperature, we know the condenser pressure should be 33.6, should be maintained at 33.6, and then we know the reboiler temperature should be at 148 degrees centigrade, should be at 1. So press next. Reflex ratio, let's put 1.75. Done. So what we need to do now, if we press run, we will have some values are missing, so let's close it. Go to monitor. So we don't have distillate rate, so uncheck it, and then let's let's add some specifications so that your top product should contain say like 99.5% pure vinyl chloride monomer. Okay, so add spec, component fraction, add spec, and then so this is for the stream 22. So select stream, target type stream, not the column. Select which stream, 22, mole fraction, specific. So let's say we need to get say 99.6% pure, for example. So 0.996. So which component is that? Is vinyl chloride monomer in the top. Okay. So close this. So everything is converged. So which means we finished the full process flow diagram. Okay. So right click, show table. This is such a big exercise, honestly. So let's add variable. Let's put mole fraction, and then select the vinyl chloride monomer, and then maybe even ethylene dichloride in the top. So done. So you can see that you can close it. So it's almost near to 99.6% pure vinyl chloride monomer in the top, and this is our condenser temperature 33.6, and the pressure is 5 atmospheres. So we can do this same thing in the bottom. So show table. So what to do? Double click on the table, add variable, click mole fraction. So let's add mole fraction of vinyl chloride monomer, ethylene dichloride, and also we have some trace amount of water. So press done. So we have some ethylene dichloride in the bottom and also some water here. Okay, so let's close this. So I think we finished the full process diagram. So let's save it. I think this is a lot of job we did, especially for distillation. I think we learned really a lot of things, especially Aspen HYSYS will help us to know to calculate the minimum number of trays and so on. Yeah. So what we can do now, so we know we have some ethylene dichloride in this stream, and then instead of wasting them, we can recycle those ethylene dichloride back to plug flow reactor. Okay, so how to do that? First save. Let me save. So whenever we add some recycle stream, it creates a big mess in Aspen. At least I don't know to fix. I always struggle. Yeah, Aspen is a good software, I shouldn't say that, but I always struggle. So let's see. So we have this ethylene dichloride, so we can add this to this PFR unit, because here we are sending the pure ethylene dichloride in order to manufacture with vinyl dichloride. Okay, sorry, vinyl chloride monomer, not vinyl dichloride. So let's do that. So to recycle some stream, all we need to do is just go to all, just type recycle, or maybe you can see this icon recycle, click that and then keep it here somewhere around here, and then your input streams should be 23. Okay, and then your outlet where we are going to let's put 24. Yeah, let's put 24. So now we are going to take this 24 and then connect it to plug flow reactor, which is here. So we can add one more stream, so let's put 24. Okay, it's converged. So we recycle back our ethylene dichloride. Okay, still it's calculating for this distillation column. I don't know, is there any error or it's calculating something? I don't understand what's happening now. Anyway, I saved the file, so I shouldn't worry. I can close this and reopen it. These parts are fine, so this should be fine too. Okay, I don't know what's the problem now exactly. So let's delete this stream. Let's delete this stream and then press active. Let it simulate one more time and see what's the problem. Okay, now everything looks fine. So when I recycle, something is happening. The stream contains only ethylene dichloride. So what is the problem exactly? Okay, I know what is the problem. Yes, you see here the stream 17. This is maintained at a temperature of 550 degrees centigrade and a pressure of 30 kilopascal. So whereas our stream 24 is at completely different conditions. So let's take a note of this one: 550 degrees centigrades and 30 kilopascals, 3000 kilopascals, 30 atmospheres. Okay. Okay, let's go back here. So what is this recycle stream? Let's put 24. Close this. So what is this temperature? 24. So this is something we have to pay attention. Yeah. So right click show table. So the temperature is 148 and pressure is only at. So let's add a heater. So let's put inlet is 24, outlet is 25. Let's say QE maybe 5. Oh, what is this? Why this curve looks so weird? Okay, something is funny. So 25, and then let's keep the temperature to 550 degrees centigrade. If you want, you can even add a pump to increase the pressure. So let's, at the moment I'm just going to stick to 30 atmosphere directly here. So everything is converged. So what we are going to do, we are going to connect this stream 25 to the plug flow reactor or the pyrolysis chamber. So now everything will be fine. So double click. So if you see here inlet, if you see the stream 17, it has ethylene dichloride. So we are going to add few more ethylene dichloride, yeah, which is recycled from this stream. So, and also have a note of this value, molar flow rate 430. Maybe I can take a snapshot of this before recycling. Okay, so before recycling, So this is before recycling. So after recycling, we will see the molar flow rate will slightly increase, which means the productivity is slightly increasing. Yeah? So that's the meaning of that. So that's the main reason we are recycling the materials. And also we are trying to make the loop as close as possible. Yeah? So let's minimize this. So close this one. So 148 so far. Good. No, what is this? Okay, this is 24. So stream pressure 25. So let's go to PFR, our pyrolysis chamber. Double click on this one, and then add our stream, our new stream, which is 25. Okay, now what's meant by unknown due? It will solve anyway. Okay. Yeah, now you see everything is solved completely, because it will suddenly it will have this temperature shock from the recycle stream. Yeah, so now everything looks fine. Everything is recycled. So let's put the recycle stream down to make it clear. And if you see the molar flow rate here, now it's 566.8. What was before? It was 500 and it was only 430 kilomoles per hour. Yeah, so let's after recycling. So in your report you have to clearly mention all these things. If you are recycling something, how the productivity changes. So after recycling, the final column. Where is my favorite tool? Snipping tool. So just we are learning now, yeah, bit by bit. So now you know the usefulness of recycling the materials, intermediate products, in this case which is ethylene dichloride. So after recycling, so clearly this is a massive increase. So kilomoles per hour. So if you convert it into kilograms, and then if you convert it into per year, that will be a big, you save a lot of money. So that will be a lot of tons of vinyl chloride monomer. Okay, so after recycling, so if let's go back to our presentation. Sorry, presentation now. Our process flow diagram. So what else we can recycle now? So we get this hydrochloric acid here, and then if you remember our oxychlorination reaction, so for that we need hydrochloric acid. Yeah, we need hydrochloric acid. In fact, we are doing this oxychlorination in order to we are doing this oxychlorination reaction in order to effectively use the hydrochloric acid produced during the pyrolysis process. Yeah, so that's what we are going to do exactly. So we take the product from, look at the big process flow sheet. We pyrolyze, and then we take hydrochloric acid. So we are going to take this HCl out, and then we are going to feed it back to the oxychlorination reaction, which is here, and then we can delete this particular stream. So because we oxychlorination is like we are going to just use the hydrochloric acid produced from the pyrolysis, and then instead of supplying new hydrochloric acid, we just use some intermediate product, and then we will close the loop completely. Okay, so that's the goal that we are going to do. So the inlet is at 25 degrees centigrade and 152 kilopascals. Okay, 1.5 atmospheres. So let's go here. So this is our hydrochloric acid. What is this composition? Okay, let's close this. This is some water and other things. So we take this hydrochloric acid. So let's add a recycle stream, add here, press all, add a recycle stream here, recycle. So now connect HCl out, and then let's put something called 26. Okay, and let's add some cooler. So take inlet stream is 26, and then outlet stream is 27. Let's put QE9, oops, QE10. Okay, QE10. So 20, close this one, and then let's put 27 is maintained at temperature of what's the starting temperature? Starting temperature is 25 and pressure is 1.5 to 1.5 atmospheres. So stream 27 is measured temperature of 25 and 1.5 atmospheres. Let me check whether I'm recording or not. I think I'm recording perfectly fine. I don't know. Let's check this. I think I am minus recording so far well. Hope there is no problem with my microphone. Let me minimize this. What we are going to do is let's close this. We are 27. Okay. Now we are going to recycle this hydrochloric acid back to the oxychlorination reaction. Okay. So double click on the mixture. So add one more input stream, which should be stream 27. Let's check. Stream 27. Yes. Okay, it's doing calculation throughout the process flow sheet, so it will take some time. So we have to wait some time. If it doesn't work, obviously we can delete the stream. Yeah. Now everything is getting converged, and finally this last distillation column. Hope we will not have any problem with this. We have some problem with two of this distillation column now. So it will take some time. You see something highlighted, which means something is happening. I believe it will be converged eventually. This is a very long exercise for you, but it's a very good exercise. Yeah. So if you manage to develop the process flow sheet, you will be really familiarized with Aspen HYSYS. I think you almost learned all the essential functions here. But Aspen HYSYS is like an encyclopedia. We can work forever, yeah, and then we can learn forever. But for within this one semester, I think whatever you are going to learn, I think whatever we did, that's more than enough. Yeah, obviously we can always advance our knowledge later whenever we have time. Even after finishing your degree, you can learn. Yeah, there is no limit for learning. Just waiting for the solver to converge. The solver is still running, that's what I see. think it will take some time, maybe a lot of time, I think. So if you see here how our process flow sheet looks, it's a really massive one. Huh? We really managed to build such a big process flow sheet. Not a bad thing. It's a really massive one. Yeah? So what we did is we did some direct chlorination, oxychlorination reactions. We take the ethylene dichloride and then we try to purify it to 99.5% pure. So we also learned to add a column separator and then some liquid extractor. And this one we did it in five stage liquid extraction. Yeah. And then this is both a catalytic process. One we modeled using conversion reactor, another one we modeled using plug flow reactor, and we already know how to add a CSTR and add the reaction kinetics and so on. If not, you have to watch lecture 3 or 4. And then we added, we collected the product stream. We try to purify them. We take the ethylene dichloride and then we try to get pure ethylene dichloride. And sorry, I got a call. So what we did, so we collected the ethylene dichloride that may contain some impurities. So we tried to purify them. This is a column separator, and then we did some 5-stage liquid extractor. So these things are really essential, especially many of your projects you may encounter with this type of unit operations in the final year, and also for this module as well. So and then we try to use a reboiled absorber. So we really learned a lot of major unit operations and some minor unit operations like a compressor, cooler, and some heater, and somewhere we also used some valve, pressure releasing valve, and then we also used a splitter as well. All these minor unit operations. And then we took the pure ethylene dichloride, we put it in the pyrolysis chamber, which is here, and before that we have to raise the temperature to some 550 degrees centigrade and some 30 atmospheres, and then we try to pyrolyze them. Still some simulation is running. I can see that the color changing, blah blah blah, from one to another. Yeah. And then we again have to quench the stream. So if not, we will end up with product degradation. And then we decided to purify the vinyl chloride so to 99.5% purity level. And then so how we did that? So we added 2 distillation column, and then 1 distillation column to separate hydrochloric acid from the remaining components, and then and also we know this hydrochloric acid. And before that we also try to give some justification, like why do we need to go for a distillation instead of other unit operation, instead of absorption or extraction. Why do we need to go for a distillation column? And then we gave a justification based on the fluid properties of all the 3 individual components involved in this particular system. And then based on that we realized, we even generated some nice graphs like that, like this. Like these are the fluid properties, and we also checked the load, the condenser load, and then the load in the reboiler using some case studies. And then we also learned all the methods involved to design the distillation column. Like we started with the component splitter, and then we added a shortcut distillation column in order to know the minimum, something like here, like where is that slide? So we added a component splitter, and then we added a shortcut distillation column in order to get all the required information, like our condenser temperature, our reboiler temperature at some fixed pressure, known pressure, number of trays, where our the feed stage, everything we learned using Aspen HYSYS. So at the moment we are trying to recycle all the process stream. So still something is going. This distillation column is converged already, so only this is the final one, which is some calculation is happening at the moment. So this is the power of Aspen HYSYS. You see, like we added some new stream in one end, and then it's performing all the mass balance calculations for us, obviously, and then it's also doing a lot of calculations for us, yeah, within in no time. So probably maybe if I allow 5 more minutes, everything will be converged. So this is something that we really need. So obviously in your design project, sometimes you may need to do it manually. You can calculate for shortcut distillation method, we can do it manually, yeah, but on the other hand, we can use software, and then we can also compare the results here and there. So why not? So I think this is good. And then what I will do is, like I think for this module, this is whatever the knowledge that we gained so far. That's more than not more than enough. That's sufficient, I will say. And then I will take some of these reactions, and then we will use different type of reactors. We already know CSTR is not working for us because of the probably we need a better reaction kinetic expression. Okay. And then probably what we need to do, so we will try to add different type of reactor, and then we see the outcome. And then one more thing we can do is let's design some plug flow reactor with some horribly complex kinetic expressions, so that those things you should know how to do using Aspen HYSYS. So probably in 2 more lectures we may cover those type of or those topics, yeah. So let's see where our simulation is running. Still something, yeah. Okay, let's wait, or maybe I can pause. I can stop recording the videos, and then T103 not solved. This is here. Why it's not solved? Oh yeah. What's this 121? This is at 60 kilopascal 5. This should work for some reason. I don't know what's the problem. I'm doing it manually. No audio detected. Okay, I stopped talking. It says it's solving, and okay, it says unconverged, and honestly I really don't know why. Component fraction is 0.995. So what's this one? Molar flow rate 21. So let's see the component analysis. Add variable. Let's put molar components. If it doesn't work, we can delete the recycle stream. Probably we can fix it later, but for this lecture it's enough. Yeah, I don't want to complicate the things. Vinyl chloride monomer, methylene dichloride, water, HCl, done. So we have a vinyl chloride monomer, water, and ethylene dichloride. So I don't know what's the problem. So It's solving. I don't know what it's doing. Okay, let's put it back to 60 degrees centigrade. So what I'm going to do is I'm going to delete the recycle stream, and then this is something. Okay, I'll delete the recycle stream. Maybe I think this is enough for this particular lecture, and then if it's necessary, then we can come back to this topic later, like integrating this stream 26. Where is stream 27? I couldn't see the stream 27. So let's delete it. So let's keep the loop open, and then so this will solve everything without any issues. Still doing some calculations. So I'm going to stop recording. I think I already showed you until the end. I already showed you how much mass we can produce, and we also checked what's happening before and after recycling here. Yeah, I think that should be enough. I'm not going to wait until this system converges. So you can try it yourself in the home. I will save this file, and if required, maybe I will give it to you during the lecture time. Thank you. Thanks for listening, and sorry for really such a long lecture. Yeah, this is okay. We developed one process flow sheet, but we learned almost all the unit operations involved in Aspen HYSYS, and we try to connect the different unit operations, and also we try to connect some major unit operation. We also learned how to recycle some stream back into the process. Okay, so I will save this, and then I will stop recording. I will edit so that I will try to minimize the time, the length of the video, yeah, to reduce the length of the video, so that you will not spend a lot of time. Okay, so I think that should be a good idea. So I will stop the recording now. So thanks for listening.